Welcome back. So we were talking about the SVRG algorithm, which is a method that leverages control variance and variance reduction to improve upon SGD. However, when it comes to training deep learning models, there are some issues and incompatibilities that basically means we're not necessarily going to use SVRG in practice anymore. The issues we talked about in summary can be attributed to the epoch-based structure of SVRG, meaning that we update the reference point once in a while after the end of each epoch, and also the finite sum assumption. Okay. Now we want to basically come up with another method which still uses this idea of, let's say, control variance to reduce the variance, but is also provably better than SGD and SGD with momentum, and is also application friendly. Okay. So let's talk about this epoch-based structure and its issues. Okay. So we want to get rid of that completely. Okay. So in particular, we don't want to update the reference point once in a while, which necessitates having an epoch-based structure. We want to update it on the fly in each iteration. Okay. So, and there is a simple way to do this, we talked about before. So if I set VE to be WT, I'm updating on the fly in each iteration and everything's good. Except this is going to be too costly because that requires calculation of a true gradient. So you have to go over the entire data. The method basically reduces to gradient descent. So we don't want to do this, okay? So we don't want to be therefore precise, but maybe we can be imprecise. Maybe we can use some approximation. Okay, so that's our main idea. And our solution is to therefore use what I refer to it as approximate control variance. Okay, so this is a control variance estimator we talked about before. So again, we want to estimate some quantity f. We had access to an unbiased estimator G. And then we said that let's consider x and y such that they have the same mean and form this estimator. Okay. Now, this condition meant that we actually needed to calculate the true gradient at the reference point. So this is the condition we want to relax. Okay. So we're going to relax it and only require that the means are approximately the same. Okay. So what's the implication? If they are approximately the same, the implication is that we're gonna incur some bias. Okay, so we're gonna incur some bias, but hopefully not too much, such that we still have this negative correlation we talked about before, and therefore a reduction in variance. And hopefully we can control this trade-off between bias and variance by finding a good beta. Okay. So this is exactly like bias variance trade-off. Okay, we talked about bias variance trade-off before in the context of SGD momentum. Okay, so a natural question therefore is there any connection between approximate control variance and momentum or not? And in fact, the answer is yes. Okay, so let's recall our SGD with momentum update vector. So this was the update vector we defined for SGD with momentum. Every time you take you basically do an exponential average over the stochastic gradient you've incurred, or put it differently but equivalently, you take a convex combination of the current gradient and the previous momentum, okay, and use that as your update vector. All right, let's do a rearrangement, okay. I want to write this down in the form of the control variance estimator. So if you do a rearrangement, not too difficult, this is what you'll get. Now this is exactly like exactly in this form. Okay, so I have an unbiased estimator of my true quantity, which is the true gradient, some parameter beta, so this and that, and then I have x, which is the previous momentum, minus y, which is again the current gradient, okay, x and y. So naturally, as we talked about before, m has some bias. It cannot, it is not an unbiased estimator of the true gradient at WT at time t. Okay, So therefore, there will be some bias here. Okay, but nonetheless, therefore, this has the form of control variate, and given that x and y don't have the same mean anymore, this becomes approximate control variate. So therefore, SGD with momentum is essentially doing approximate control variate. Okay, and this is exactly why it reduces the variance to some extent while incurring some bias. Okay, what we talked about before. Okay, and again, the reason for that is that it is using control variates. There is sort of a negative correlation, if you will, between this part and this part, which results in the reduction of the variance. Okay. Okay. Now we talked about this method before. We talked about a convergence guarantee, and we saw that in the worst case, it's not beating SGD. Okay. Now we want to basically alter this method slightly, such that we find like a better algorithm, if you will. Okay. So let's discuss this a little bit intuitively to gain some intuition and see whether we can leverage this intuition to come up with this better algorithm I'm talking about. Okay. All right. So intuitively, m sub t minus 1. Okay. So it's the momentum at time t minus 1. So therefore, this should be a good estimator of the gradient at time t minus 1. Okay. However, this stochastic gradient is a stochastic gradient at wt, model at time t. So it should be a good approximation of the true gradient at time t. Okay. So you see, there is like a time difference. Okay. So maybe we can get rid of this time difference such that we basically reduce the bias estimation error and therefore improve the convergence guarantee of the resultant algorithm. Okay. So this is what we're going to do, right? But for the case of SGD with momentum, if we assume that the evolution is slow, such that model at time t minus 1 is exactly the model at time t, therefore a good approximation of the gradient at time t minus 1 is also a good approximation of the gradient at time t, exactly like approximate control variant. Okay. Now we're going to use this discussion, basically the fact that m t minus 1 is a good, again, estimator at time t minus 1, whereas the stochastic gradient is a good estimator of our quantity at time t, to develop a better algorithm. Okay. All right. In particular, we want to basically debias the SGD with momentum. Okay. We talked about the debiasing before. And in that context, which was a highly imprecise but nonetheless useful discussion, we saw that when we update the momentum, we may want to divide it by this factor to reduce the bias. But again, in our discussion, we were very imprecise. We made lots of assumptions that were not necessarily true. So here we're going to try a different debiasing idea, which turns out to be highly effective and in fact leads to very good convergence guarantees. Okay. So recall our discussion. M t minus 1 is a good approximation of our quantity at time t minus 1, while this guy is a good approximation of our quantity at time t. There is this time difference, so we want to get rid of it. Okay. So in particular, is it possible to change this gradient to something that is a good approximation of our quantity at time t minus 1 as well? Okay. And yeah, there's a candidate. So let's use. I'm missing the gradient symbol here. So a candidate is the gradient at, instead of wt, we use the gradient at wt minus 1, or rather the stochastic gradient at wt minus 1. So therefore, this is going to be our method, the debiased SGD with momentum, if you will. Okay, second attempt. So we use our usual update. We go from the current solution to the next one by following the direction of our update vector minus m. But we're going to update m, the momentum, differently. Okay. We have the stochastic gradient at wt, the momentum parameter times the momentum at time t minus 1 minus the stochastic gradient at wt minus 1. Previously, this term was the stochastic gradient at wt. So what all I'm doing is this very, very tiny change, that I'm changing this index from t to t minus 1. That's all I'm doing. Okay. All right. So let's compare this this method with SVRG next. Okay. So this is the update vector we are using. Okay. And recall, this was the update vector of the SVRG algorithm. Okay. So we are improving SVRG in some sense. Okay. First of all, we can actually interpret wt minus 1 as our new reference point compared to v sub e, something that we calculated in the beginning of epoch. Okay, so therefore the reference point is now much closer to the current solution wt. Okay, so therefore we should expect a more effective variance reduction compared to SVRG's estimator. Okay, so that's one benefit. Another benefit is that we are not calculating any full gradient. So for the SVRG, we needed to calculate this full gradient outside of the epoch. Okay, but we are not doing that anymore here. We are approximating it by momentum at time t minus 1. Okay, so momentum at time t minus 1 is again an approximation of the true gradient at wt minus 1, and now wt minus 1, the previous update, is acting as our reference point. Okay. Another way we are improving over SVRG is that all calculations are happening inside an epoch. Okay, so there is no epoch structure anymore that we needed to basically calculate the true gradient outside of an epoch efficiently. We are updating the reference point on the fly inside an epoch. Therefore, we are completely getting rid of the issues with the epoch-based structure. Okay. There is a similarity between this debye associated with momentum and SVRG, and that's the fact that they both are using 2 stochastic gradients in each iteration. Okay, as opposed to 1. In the case of SVRG, we were using the stochastic gradient at the current model wt and the stochastic gradient at the reference point. Here, again, we are using the stochastic gradient at the current model wt and the stochastic gradient at the previous model wt minus 1, which is basically our new reference point. Finally, in SVRG, we used beta, which was equal to 1 exactly. Okay. In this case, given this approximation we are doing and using approximate control variate as opposed to precise control variate, we actually have to use a beta which is strictly less than 1 to make sure we are taming the approximation bias, okay, and ensuring that the algorithm does converge. Okay. All right, so it's a good segue, therefore, to talk about the theoretical guarantees for this method. Okay, so again, our usual assumptions. Let's assume that the average loss, as well as the sample loss, are both L smooth. We assume that we have access to a stochastic first-order oracle with bounded variance that returns to us an unbiased estimator of the true gradient. And also, we assume that the mini batches that we are using in each iteration are statistically independent. Then this new method that we talked about with a step size or learning rate, which is defined by this expression, 1 over t to the 1 over 3, and the momentum parameter that satisfies 1 minus beta is equal to 1 over t to the 2 over 3. So therefore, 1 minus beta is a very, very tiny number, which means that beta is a very, very large number, very close to 1. Okay. So this method is going to satisfy this condition, which basically means that we're going to find a first order solution with the rate of 1 over t to the power of 2 over 3. Okay. Let's recall the result we had for SGD and SGD momentum, and let's see how the new result compares with that. So for SGD, we said that again, I'm doing some approximation here, which is fine for the sake of this discussion. We said for SGD that the step size has to be 1 over the square root of t, and the rate we got was also 1 over the square root of t. For SGD with momentum, again, we said that the step size has to be 1 over the square root of t. 1 minus beta has to be 1 over the square root of t again. And the rate we got was, again, the worst case rate was exactly like SGD. It was also 1 over the square root of t. So therefore, this theorem is saying that we are actually getting a provably better rate compared to both SGD as well as SGD with momentum. Okay, and this is because we are basically, if you see the statement of the theorem and compare it with the with this summary result for SGD and SGD with momentum, you can see that we are actually using larger learning rates, right? So, or we are allowed to use a larger learning rate and also a larger momentum parameter. Okay, so we are allowed to use a larger learning rate, larger momentum parameter, which means faster convergence. Okay, and the reason that we can use larger learning rates and don't diverge is that due to this new construction, due to this debiasing thanks to approximate control variates, we have a reduced approximation bias. Therefore, it's not going to be as detrimental to our convergence compared to SGD and SGD with momentum. Okay, and finally, recently it's been shown that this is the best rate we can get. So this algorithm under this assumption is one of the optimal algorithms. It's not the only optimal algorithm, but I would say it's one of the simple ones. Okay, which has this very intimate connection to both SGD with momentum as well as variance reduction, as we discussed in the context of SVRG. All right, so I'm not going to go over the proof of this theorem. It's very, it's not involved, but it's, I would say, something we can absolutely handle using the techniques we developed in the course so far. But let's talk about the main ideas. So main idea is actually very similar to the proof of SGD with momentum. Okay. Again, we're going to consider and analyze the evolution of our estimation error or approximation error. Okay, so which was the difference between momentum and the true gradient. So we're going to do this and using our assumption and some useful inequalities, we can establish a recursion that basically is saying that the error at time t is less than or equal to beta, which is crucially less than 1 times the previous error plus some other terms. Okay. Then this was basically very similar to what we discussed in the context of SGD with momentum. And we said there that whenever you have this additional source of error, you want to construct a potential function which integrates this additional source of error. And this is exactly what we will do. We're going to construct a potential function, which is basically our suboptimality or expected suboptimality plus this estimation error. And we're going to study the evolution of this potential by summing over its consecutive differences. Thankfully, given that beta is strictly less than 1, we can find a good constant, C here, which will ensure the method converges. Okay, this again shows the very nice property of the evolution of the error. Again, thanks to the form of the estimator we are using in each iteration. So there you go. This is basically, therefore, one way to mitigate some of the issues of SVRG and develop an algorithm which is actually provably better than SGD and SGD with momentum. It has, in terms of the structure, it is very similar with SGD with momentum with minor differences. So therefore, it's something that we can actually use more frequently in practice compared to SVRG, and still benefit from the elegance and theoretical benefits of variance reduction. All right, so this is basically the end of our section on advanced training algorithms. When it comes to, again, training an optimization model in a centralized scenario where all the data points are in one place. In the next lecture, we're going to start talking about other learning paradigms, which we refer to as distributed learning paradigms and distributed learning. I'll see you there.